So I am Sophie F. Marian Terb, along with my members, Shalu I. Francis, Tyrell F. Fernandez, Albert R. Sib, James Santiago, and we will be discussing part for the electrical methods for analysis. So we already know that atomic is an electrical method that is based on measuring quantity to convert analyte to oxidation state. And now we will be discussing the types of coulometry. So first one here is potential coulometry, also known as potential stat. So this controlled potential coulometry determines the quantity of substance sample by measuring the amount of charge required to convert it to another substance through a redox reaction. So this technique is particularly useful for analyzing substances that undergo irreversible reactions, as well as for determining the substance or concentration of an analyte sample. It is commonly used in electrochemical analysis and be applied in various fields, the environmental monitoring, pharmaceutical analysis, and qualitative in industrial processes. So in control potential, a constant potential is applied to the working electrode, typically a chemical like platinum, while the current that is measured, and as the reaction progresses, the amount of charge that passes the cell is directly proportional to the quantity of substance being analyzed. The potential of the electrode is maintained at a constant value, and the current is recorded as a time. So there are important parts of control potential from. So first one, electrolysis cell, the potential stat, and the. So for the electrolysis cell, it's actually caused by electrochemical cell where the reaction occurs. A working electron which is an inert like platinum. For general cases where the elements are easily reduced, mercury is actually mostly. Next is a counter electrode, which completes the electrical circuit cell, and it is often used by conductive metals like platinum or graphite. A reference electrode that contains the constant potential against which the potential is measured, and a common reference electrode that is saturated calomel electrode or the silver or silver chloride. Next is the potential stat. So this instrument is used to control the potential applied to the working electrode, and it maintains the constant potential between the working electrode and the reference electrode. And last but not least is the electrode, which measures the current flowing through the cell as a result of applied potential. And this typically records the current time.
A second approach to coulometry is called controlled current coulometry. This is also called coulometric titration as it is similar to other titiometric methods. This analysis is based on measuring the combined capacity of the analyte with a standard reagent. In the coulometric procedure, the reagent consists of electrons and the standard solution is a constant current of known magnitude. Here, electrons are added to the analyte via the direct current or to some species that immediately react with the analyte until an endpoint is reached. At that point, the electrolysis is discontinued. The amount of analyte is determined by the magnitude of the current and the time required to complete the titration, wherein the magnitude of the current in amperes is analogous to the molar concentration of a standard solution. and the time measurement is analogous to the volume measurement versus volumetric titrimetry. The equipment required here includes a source of constant current from 1 to several hundred milliamperes, a titration cell, a switch, timer, and a device for monitoring current. As shown in this figure, moving the switch to position 1 simultaneously starts the timer and initiates a current in the titration cell. When the switch is moved to position 2, the electrolysis and the timing are discontinued. With the switch in this position, however, current continues to be drawn from the source and passes through a dummy resistor that has about the same electrical resistance as the cell. This arrangement ensures continuous operation of the source, thus aiding in maintaining a constant current. This figure shows a typical coulometric titration cell consisting of a working electrode at which the reagent is produced and a counter or auxiliary electrode to complete the circuit. The working electrode used to generate reactants is often referred to as the generator electrode. It is usually a platinum rectangle, a coil of wire, or a gauze cylinder with a relatively large surface area to minimize polarization effects. The counter electrode is usually isolated from the reaction medium by a sintered disc or other porous medium to prevent interference by the reaction products from this electrode. Volumetric titrations, like their volumetric counterparts, require a means for determining when the reaction between analyte and reagent is complete. Generally, the endpoints on volumetric methods are applicable to colorimetric titrations as well. For example, in the titration of iron 2, an oxidation or reduction indicator can be used. As an alternative, the endpoint can also be determined potentiometrically or amperometrically. These are used in Karl Fischer titrators. Some colorimetric titrations also use a photometric endpoint. In this part of the discussion, we will now discuss the comparison between the two methods.
So one of the many advantages of potential coulometer, it is highly precise, particularly for samples with concentrations or small, and it is also versatile, which means it can be applied to a wide range of analytes in organic organic compound. The setup for control potential coulometer is relatively simple to other analytes, and it is suitable for analyzing substances that undergo reversible reactions. It is also flexible because it can be applied to samples of various sizes, allowing for both small and large sample volumes. So the disadvantages of controlled potential coulometry are the limited sensitivity, since it may not be as sensitive as some other analytics, particularly for gas level analysis, where extremely low concentrations need. Electrode fouling can occur over time, especially if analyte or reaction products adhere to the electrode surface, which can affect the accuracy and reproducibility of the measurements. Interfering substances present in the sample can also affect the accuracy of analysis by contributing to the measurement, leading to potential errors in quantification. The choice of electrolyte and its concentration can also influence the performance of controlled potential coulometry, requiring careful selection and optimization. And lastly, while the setup for controlled potential coulometry is simpler than others, specialized equipment such as potentiostats and electrodes can be costly, especially for high performance apps.
A controlled current coulometry has two advantages over controlled potential coulometry. First, the analysis time is shorter because the current does not decrease over time. A typical analysis for controlled current coulometry is less than 10 minutes compared to approximately 30 to 60 minutes for controlled potential coulometry. Second, because the total charge is simply the product of current and time, there is no need to integrate the current time curve. However, using a constant current leaves us with two important experimental problems. First, during electrolysis, the analyte's concentration and the current that results from its oxidation or reduction decreases continuously. To maintain a constant current, we must allow the potential to change until another oxidation reaction or reduction reaction occurs at the working electrode. Unless we design the system carefully, this secondary reaction results in a current efficiency that is less than 100%. The second problem is that we need a method to determine when the analyte's electrolysis is complete. In a controlled potential analysis, we know that electrolysis is complete when the current reaches zero, or when it reaches a constant background or residual current. In a controlled current analysis, however, the current continues to flow even when the analyte's electrolysis is complete. A suitable method for determining the reaction's endpoint is needed.
So when do we apply controlled potential coulometry and controlled current coulometry? If we were to analyze inorganic cations and anions, including traces of metals and halides, analysis of alloys, traces of uranium and polonium, and organic compounds, we can use the controlled potential coulometry. However, the organic application of this method is much less significant compared to the inorganic application. Now, if we were to analyze proteins and analytes that can be analyzed through colorimetric redox titration such as oxalic acid, hydrogen sulfide, iron complexes, thallium dichromate, astatine, and the like, then we use the controlled current coulometry. Here's an example of the application of colorimetric methods. The problem is, the purity of a sample of sodium thiosulfate was determined by a colorimetric redox titration using iodide as a mediator, and triiodide ion as the titrant. A sample weighing 0.1342 grams is transferred to a 100 ml volumetric flask and diluted to volume with distilled water. A 10 ml portion is transferred to an electrochemical cell along 25 ml of 1 molar potassium iodide, 75 ml of a pH 7 phosphate buffer, and several drops of starch indicator solution. Electrolysis at a constant current of 36.45 milliampere required 221.8 seconds to reach the starch indicator endpoint. Determine the purity of the sample. Now, we list the given of the problem, which are the current, which is 36.45 milliamperes or 0.03645 amperes, the number of electrons, which is 1 mole of electrons, the time, which is 221.8 seconds, and the molar mass of the sodium thiosulfate, which is 158.1 grams per mole. Presented on the screen are the formulas to be used in the problem. Now that we have the formula to be used in solving this problem, which is mass of analyte is equal to the current multiplied by time multiplied by the molar mass divided by the product of the moles of electron and Faraday's constant. We now have to plug in the values of the given we have listed earlier. Plugging in the given values, we will get 0.01325 grams of sodium thiosulfate. We will multiply the mass of analyte in the 10 ml alico by 10 since the original volume of the sample is 100 ml. For the purity, we will divide the mass of the sodium thiosulfate obtained from the analysis, which is 0.1325 grams, to the mass of the sample, which is 0.1342 grams. We multiply the quotient by 100% to get the purity of the sample, which is 98.73% sodium thiosulfate. So here's another example for the application of colorimetric methods. The problem is a 0.3619 gram sample of tetrachloropiconilic acid is dissolved in distilled water, transferred to a 1000 ml volumetric flask, and diluted to volume. An exhaustive controlled potential electrolysis of a 10 ml portion of this solution at a spongy silver cathode requires 5.374 coulombs of charge. What is the value of N for this reduction reaction? Now, we list the given in the problem, which are the charge equivalent to 5.374 coulomb, mass of analyte, which is 0.3619 grams for 1000 ml portion, and 3.619 milligrams for the 10 ml portion, and the molar mass of the sample, which is 260.878 grams per mole. From this, we will use the formula moles of electron is equal to the charge over the product of the moles of analyte and Faraday's constant. Plugging in the values, we will get 4 moles of electron. The result means that to reduce a molecule of tetrachloropiconilic acid, it will require 4 moles of electrons.
And now, let's discuss the voltammetric methods of analysis.
So, voltammetry is a method in chemistry used to study how substances respond when electricity is applied to them. So, imagine a solution containing a substance under investigation. A specialized electrode known as a working electrode is immersed in the solution, and voltage is applied using a device called a potentiostat. This voltage prompts some substances in the solution to undergo changes, potentially gaining or losing electrons, leading to an electric current flow. This current provides insights into the reactions occurring in the solution. Unlike applying a constant voltage, in voltammetry, the voltage is varied over time. It might gradually increase, decrease, or shift back and forth. These voltage changes allow observation of how the current varies accordingly. The patterns observed in the current, known as voltammograms, offer valuable information about the properties of substances in the solution. For instance, they can reveal substance concentrations, reaction rates, and even the types of substances present. In essence, voltammetry helps scientists comprehend how substances interact with electricity, aiding in the study of chemical reactions and the analysis of substances in solutions.
And for analytical purposes, various forms of voltammetry are utilized. Stripping voltammetry is particularly notable for detecting trace amounts of metals in the environment. Meanwhile, techniques like differential pulse polarography and rapid scan voltammetry, such as cyclic voltammetry, are essential for identifying pharmaceutical species. So let's discuss them one by one. So first, stripping voltammetry. Stripping voltammetry is like a detective searching for trace amounts of metals in a solution. Picture a solution with various metals, but you're after one specific metal, like lead. To isolate it, you employ a stripping voltammetry technique. First, you immerse a specialized electrode into the solution, acting like a magnet for lead ions. Then, you apply a small electric current, causing the lead ions to adhere to the electrode. Next, you reverse the current, prompting the lead ions to be stripped off the electrode and released back into the solution. By measuring the amount of lead returning to the solution, you can determine the original lead concentration. This method is akin to using a magnet to catch metal traces in a pond, offering precise detection even in complex solutions. It's invaluable for identifying metal pollutants in the environment or analyzing metal content in medical samples. So next is the differential pulse polarography. So differential pulse polarography is a precise electrochemical technique for analyzing substance concentrations in a solution. So here's how it works. Imagine you submerge a working electrode, often made of glassy carbon, into the solution containing the substance of interest. Then, instead of applying a steady voltage, as in regular polarography, you apply a series of small voltage pulses atop a baseline voltage. Each pulse is brief and low in amplitude. After each pulse, you measure the resulting current. By comparing these currents with the baseline, even subtle changes can be detected accurately. This meticulous method enables scientists to determine substance concentrations with remarkable sensitivity and accuracy, even amidst other substances in the solution. And last is cyclic voltammetry. Cyclic voltammetry is a widely used electroanalytical technique, especially in studying oxidation or reduction reactions and detecting reaction intermediates. Imagine a solution containing a substance under study. You introduce a working electrode into the solution and apply voltage. As voltage application begins, you observe fluctuations in the current passing through the electrode, indicating oxidation or reduction reactions of substances in the solution. Unlike applying a constant voltage in cyclic voltammetry, you sweep the voltage back and forth in a repeating cycle. Starting at a low voltage, you gradually increase it to a maximum, then reverse the direction, decreasing it back to the starting point. This cyclic voltage variation produces characteristic current patterns called voltammograms. These patterns offer valuable insights into substance behavior, revealing reaction kinetics, substance concentrations, and other essential properties. In essence, cyclic voltammetry involves oscillating the voltage applied to an electrode in a solution and monitoring resulting current changes, aiding scientists in understanding electrochemical substance reactions with precision.
In this section, we will discuss how quantitative and qualitative information may be extracted from a voltammogram. But first, let us know what is a voltammogram. In simplest terms, a voltammogram is described as the electrochemical equivalent of a spectrum in spectroscopy. It is essentially a plot of the current I flowing through the electrochemical cell versus the applied potential at the working electrode. Hence, we can also use it for analysis to gain quantitative and qualitative data about the species involved in the oxidation or reduction reaction. First, we can use voltammogram to extract quantitative information, which is obtained by relating current to the concentration of analyte in bulk solution. So to determine concentration, assume that the redox reaction at the working electrode is given by the equation O plus Ne minus producing R, where O is the oxidized form of the analyte, Ne is the number of electrons in redox reaction, and R is the reduced form, assuming that initially only O is present in the bulk solution. The current is determined by the rate at which O diffuses through a fixed diffusion layer, which gives us the following equation, where K sub O is a constant equal to N FAD over delta. So when the limiting current is reached, the concentration of O at the electrode surface is 0. Therefore, we can simplify the solution into this. Thus, the limiting current, I sub lim, is a linear function of the concentration of O in the bulk solution. Using the voltammogram, a quantitative analysis is possible using any standardization methods
such as when using reagents as standards, single and multiple point standardizations, external and internal standards, and lastly, standard addition. Furthermore, voltammogram can be used in various fields. For example, for environmental samples, voltammograms can be used in analysis of trace metals. The most common samples are natural waters. Concentration of trace metals at parts per billion level and parts per trillion level is made possible. In clinical applications, it can be used to determine the concentration of trace metals in a variety of matrices, including blood, urine, and tissue samples. Other applications of voltammetry involves analysis of trace metals in other samples, including food, steel, and other alloys, gasoline, gunpowder residues, and pharmaceutical. In pharmaceutical industry, it is used to determine concentration of drugs and vitamins in formulations. However, to ensure proper and accurate analysis using voltammetry, it is important to select appropriate voltammetric technique and correct residual current before analysis. The choice of which voltammetric technique to use depends on the sample's characteristics, including the analyte's expected concentration and the location of the sample. In any quantitative analysis, the signal due to the analyte must be corrected for signals arising from other sources. Just to give you an idea, here's a quick rundown on the common voltammetric techniques. First, we have polarography, which is known as the earliest voltammetric experiment. It uses a dropping mercury electrode or a static mercury drop electrode. In normal polarography, the potential is linearly scanned, producing voltammograms like what you can see in the graphs. Normal polarography has been replaced by various forms of pulse polarography, several examples of which are normal pulse polarography, differential pulse polarography, staircase polarography, and square wave polarography. Similar with polarography is hydrodynamic voltammetry, which shows identical resulting voltammograms. In hydrodynamic voltammetry, current is measured as a function of the potential applied to a solid working electrode. It also has the same potential profiles used for polarography, but because hydrodynamic voltammetry is not limited to mercury electrodes, it is useful for analysis of analytes that are reduced or oxidized at the more positive potentials. One of the most important quantitative voltammetric techniques is stripping voltammetry, which is composed of three related techniques: anodic, cathodic, and absorptive stripping voltammetry. Seen in the slide is the anodic stripping voltammetry. Another technique is called amperometry, a form of voltammetry in which we measure current as a function of time while maintaining a constant potential. An important application of amperometry is in the construction of chemical sensors. Seen in the screen is one of the first amperometric sensors that was developed for the detection of dissolved oxygen in blood, developed in 1956 by L.C. Clark. Voltammograms can also be used for qualitative applications, such as by determining the standard state potential for the redox reaction. To extract the standard state potential or formal potential, we will still assume to have the same redox reaction at working electrode given by the formula O plus Ne minus equals R. To extract the standard state potential, we need to rewrite the Nernst equation in terms of current instead of concentration of O and R, which we can use to get the formula for the concentration of O, which is equals to limiting current minus current all over K sub O. This will be our equation 1. Similarly, we will derive similar equation for concentration of ore at electrode surface. It is important to note that the concentration of R in bulk solution is 0. We can therefore simplify our equation into equation number 2, which is concentration of R equals to current over K sub R. Using our equation 1 and equation 2, and substituting into the Nernst equation, we have our final equation, and it can be further simplified if the given current is half of the limiting current. In this case, we will use this second equation, where E sub 1 half is represented as half-wave potential. This equation is only valid if the redox reaction is electrochemically reversible. Voltammetric techniques giving fixed potential can also be used to determine a redox reaction's standard state potential.